the official welcome word will sort of be given this afternoon. So, we're going to just begin with the first talk of the day by Brian Turner from the BAE system. And he's going to be talking about finding a solution to complete urban propagation modeling in our lifetime.
Good morning, everybody. Just to start off, I want to make a couple of remarks. This is not so much about talk about mathematics as it is a cry for help. I'm a physicist. I work as a system engineer. I know nothing about mathematics, so really I'm going to be talking about problems, not solutions. But I need to be honest with you, even though it is a cry for help, we're kind of both taking this in the sense that if you decide to help me, I may not be able to pay you. But if you do find a solution, you may be able to take this to another bidder. And because I'm so worried about the content of my talk and whether it's going to be useful to you, I'm going to tell you a joke first, at least you'll get something out of the morning. And it's about a set of triplet brothers. By the circumstances that these stories are always told, they have identical apartments on the same night, identical fires break out in their apartments. It turns out the first brother is a physicist who looks at the fire, designs a very complicated apparatus to titrate the correct amount of water to extinguish the fire, writes an MSF grant to get the money to build the apparatus, and finally, carefully puts out the fire. The second brother is an engineer who sees the fire, gets his engineering tables out, looks at a solution, writes a program plan, and uses two times the amount of water necessary to put out the fire and extinguish the fire. Now you got to know where this is going, right? The last brother is a mathematician, and sees the fire and looks at the fire and realizes that there's a closed form solution to extinguishing the fire and goes back to sleep. Now, if I really believed that, I wouldn't be here, because this set of talks and the center here really is a great resource for solving real problems in the world. And so that's what really the kind of spirit of what I'm trying to present here is a real problem that has a real effect on people. I'll give you a quick introduction to who BAE Systems is. BAE stands for British Aerospace, although in North America it's a wholly owned subsidiary, so we can actually do work for the Department of Defense. The big BAE in North America does all kinds of things, platform solutions, does some armored vehicles, signal intelligence packages, communication packages for the military. Locally, in the Advanced Technology Group, which is in Washington, D.C., we're a fan of work. We're skunk works. We're trying to be on the bleeding edge, trying to get new capabilities. It is not often that many of the ideas that we have get fielded, but it does happen. For example, this set of rod armor is one of the most effective ways of feeding roadside bombs in Iraq right now. That's something that we developed at BAE. But it's lightweight, and we can't keep up with the demand right now. So, that kind of thing, it was a simple thing, but it's saving lives today. This picture is a picture of a very low frequency antenna array in Alaska that's used for both atmosphere physics and also some underground remote sensing. And if you believe all the stories on the internet, it's also used for mind control. The particular group I'm in is the RF Technologies group, and we're in Reston. We do communications technologies. We've developed some interesting radio platforms. We've also worked on a lot of DARPA programs on geolocation, signal intelligence, a couple other things that I'd have to show you if I told you. And so we have a wide spectrum of capabilities, but what we really don't have in our company is people that know how to do some of the kind of advanced mathematics that you know how to do. And so let me tell you about a problem that we'd like to solve. I took this slide from a DARPA PM, Dr. Michael Zatman, who's talking about the problem of communications in urban situations. I'll let you read it, but I'll talk around it in that today, if we send our armed forces into a search and clear mission in Iraq, an urban city, The group of guys that are outside the building cannot communicate with the group of guys inside the building, simply because it's so hard to get through walls with the equipment that we have. And it's costing us lives. Some guys will actually go and buy digital radios, drop one by the door so they have a relay station. Okay. So we don't have good solutions in the field right now for this kind of problem. So it's an SNR problem. This isn't a multipath problem. It isn't an interference problem. It's just simply that we can't get enough power to the receiver. And the standard solution, what a typical engineer would do is figure out the link budget, how much power do I need to get to point A and point B, and I'm going to add 10 dB more power to make sure I can cover myself or anything. The problem is that a standard deployed soldier, a foot soldier right now, sometimes carries up to 20 pounds of batteries. 20 pounds of batteries. That's not even his body armor, that's not his weapons, that's not anything else. So to ask him to carry more batteries, him or her more batteries, it's not really a responsible thing to do. So we have to find a way to get the communication systems to work in these urban environments without upping power. There are smarter ways. Our group has a DARPA-sponsored program called Deep Speed, which actually has 3 technical nuggets, although I'm only going to talk about 2 today. And I'll talk about these nuggets in a moment, but underneath all of these things is we need to know beforehand what we think the propagation channels will be in the environment. So to the extent that we can model what is the loss between point A and point B, or at least the predictable loss between point A and point B, we can more effectively implement these solutions. So this is kind of a fancy picture of an urban combat situation where we can have people all over on tops of rooftops in the city, or even into bunkers. And we're trying to develop technology that allows us to penetrate into all these things. So if we look at the loss as a function of distance, we see this very fast wiggling loss function, which is unpredictable. It could be from vehicle traffic, it could be from people traffic, it could be from weather, it could be from foliage, it could be all these things, and we'll never ever be able to predict it. It just won't happen. And then we have this predictable. There's a building in between you and I. There's down the stairwell, those types of things. So if we look at knowing that these things happen, and this doesn't even talk about multipath yet, there are a couple things that we can do. If we know that when you turn a corner and you're talking to me, there's going to be a 30 dB drop in the signal, I can preemptively reroute the transmission to a more advantaged node if I know where you are and I have an idea of what your trajectory is. And so we can use predictive networking techniques to basically proactively reroute. I'm not going to talk much about that today. I can also use lower bit rate communications, in this case synthetic speech encoding, where the speech fragment is cut up into phonemes, basic sounds. And that phoneme can be then represented by a couple bits. And so instead of having this waveform, I've now shrunk that waveform into a couple bits. Now that my bit rate's way down, I can send communications more reliably with the same power. The problem with the synthetic speech encoding is that it sounds like a robotic voice. The other technology that we can use is a multi-layer waveform. With the multi-layer waveform, what we do is redundantly encode the information. So at the top layer, I have a very fast, high bit rate vocoder. Underneath it, I have a medium rate vocoder. And underneath that, I have my synthetic speech encoding. They're all time synchronized, and I put enough energy into each one of them, so I know that 99.99% of the time, my synthetic speech will get through. And then I start rolling the dice a little bit with the medium and the high layer. So what will happen is if there's a sudden an unpredictable loss, instead of hearing the high quality speech, it will cut in with the medium or the low quality speech. It turns out that this is more energy efficient in an unpredictable environment. it was a predictable environment, you would just put the energy into whatever one waveform that you need. But in an unpredictable environment, this is a better insurance policy than just turning up the power. With the predictive networking, we've shown all these things to be true, that we can get to an equivalent of a 25 dB gain in SNR. With the synthetic speech encoding, 20 dB or more SNR, and the multi-layer waveform, 10 dB SNR. And those are all additive. So we have potential of 55 dB gain in the SNR, which is a huge amount. This is just a little bit of what I just said about the multi-layer waveform. And the way that's being implemented right now is that we have a 12 kilobit per second vocoder, 2.4, and actually right now we're running around 300 bits per second vocoders. And these vocoders have been actually shown to be 95% comprehensible. So if you listen to it, you can pick up 95% of the words. And that is actually phonetic words. If you were looking at meaning, for example, if I said turn right, and you might not be able to hear right too much, but from the context you might be able to actually turn right, the comprehensibility would be higher. Okay? So we think that's a really good achievement. Now this is all really cool and all really neat, but the question is how do I spend the energy among these waveforms to ensure that the message is going to get through? And this is where I need to know what the channel loss is, because if there's no way that this signal is going to get through from here to the physics building, assuming anybody's listening over there, okay, then there's no sense putting any energy there. Okay? Then I can distribute the energy in a smart way between these two layers. However, if it's easy to get there, then I might want to spend more energy here and make sure that they get the higher quality voice. So I need to know what the channel characteristics are to really implement this in a good way. Just a little bit of bragging about our synthetic speech. Typically, it's really hard to get both good comprehensibility and low bit rate. It's actually, it hasn't been done before. And because we can actually go from 12 kilobits per second down to about 300 bits per second and still have 95% comprehensibility, we're getting over 20 dB gain in this. So let's talk a little bit about modeling. Okay. We use, and this has been kind of vetted by the Army, we use a shooting bouncing ray technique from a group in Ann Arbor. They were EMAG, now I think they spun off to EMAG Ware, who's actually making the propagation software. And it's called EMQ. So I take a 3D representation of the building, I put all the building constants, the material constants, into the database. I have a database of the terrain. And what I do is I line, and right now we're going to do outdoor propagation for this, from what I'm talking about. I basically line the area with little sample receivers. And then I put one transmitter somewhere, and I trace rays at 1 degree increments. And I let the rays propagate until the energy that is in the ray is below the receiver sensitivity. Then it doesn't make sense to track it anymore. And so there are hundreds of thousands of rays being bounced through my simulation. And then at the end, I do an accounting to see which rays intercepted the apertures of what receivers. And then I have an idea of how much energy is in each spot, or conversely, I know the loss from point A to point B. Turns out that this is a really good approximation to reality. The Army ran a competition, I think 2 years ago, for different urban propagation softwares, and these are other brand names, and it matched very well to on-the-ground measurements. So this is a really powerful and fairly accurate tool. Okay. And just to give you kind of a flavor of a simulation, This is Roslyn, Virginia. BAE has a building right there. And we put a transmitting antenna that's 25 feet off the ground, and the receivers are 5 feet off the ground, and they're spread at 5 meter intervals. Okay, and I'm just going to let the simulation run, and 8 hours later, I get a false color representation of the signal strength. And I've actually, the black areas, there's a continuum. I X'd them out or blackened them out to say this is a place where you can't see a receiver, even though it would actually calculate further down to whatever the threshold is. So that's about 8 hours of simulation. And this is fairly accurate. Okay, so here's the problem. In an urban situation, let's say something relatively small, maybe a 5 kilometer by 5 kilometer grid. It's pretty small part of the city. If I want to know arbitrarily point A to point B transmission, that means I have to run somewhere around 100,000 simulations to go. So basically, I stand here. Can you hear me now? To all my receivers. Can you hear me now? I run the simulation. And so I start stepping my way through that. If I do that, it takes me something like 81 years to do the calculation with 4 processors involved. Now, even if I went massively parallel, I'm not going to get 10 to the 5th gain in my time to a solution. That's a little bit beyond even parallel computing. Okay. To make this tactically useful, if I'm going to go in to a city, and do some kind of military operation, I need stuff that operates on a day or maybe a week, day type of calculation. Especially in a place where, I graduated from here about 20 years ago, and I can't believe the difference in the campus. If I would have started the simulation when I graduated, it'd be all wrong by now, right? Because of the way the buildings have been changed. So this is a big problem. Now, I could try to do from me to the physics building and just figure out the rays that it would get from me to the physics building. But even that case takes about 100 to 1,000 seconds to be able to do that. Again, if I want to talk to the physics building now, 1,000 seconds from now, it's not going to do it. Okay. So this is where you come in. All right. From this point on, I'm waving my hands, and it's sort of a, like the title says, a physicist turned engineer's guess on mathematics. It seems to me that compressive sensing technique should be applicable to this problem. Certainly, if I gave many of you this picture as a data set and begged you to tell me what kind of sparsity would be in it and actually how many points I would need to sample, this probably would lend itself very well to a compressive sampling type of analysis. Compressive sampling, that is, where the basis set that describes the space that you're looking at is much less than the number of pixels represented, and so you have a chance of combining your basis set, and then you use random observations to reconstruct. JPEG runs sort of on that type of thing, except it actually samples everything and then takes the coefficients and only sends the coefficients out, so it's kind of a wasteful step in the sense that it has to measure everything before it does that. Okay, so that doesn't quite solve the computation problem yet, but it does give me, and I'll tell you embarrassingly, I do a thought experiment. I like to go to the extremes. One of the extremes is what if I had no buildings, and what would be the propagation? Well, the propagation function would be sine squared x over x squared. That sounds like a pretty good wavelet representation, and I'm sure if I only sample 3 or 4 points, I'd probably have the whole picture you produce. So at least at the easy side, wavelet representation is going to be a good solution for this. And looking at this picture, well, it sure looks like to me that it's a fairly sparse basis set that would describe this. Okay. So this is my idea for what would be a notional research approach. Okay, and I did them in order of what I thought were the easiest problems to the hardest problems, but I think there has to be some linearity. Let's first use the simulation data, and there's lots of simulation data available to try to discover the discrete sparsity and what kind of basis sets are out to improve this kind of problem. Urban propagation, the scales, roads are pretty much the width of roads, buildings are pretty much the width and height of buildings, and the wavelengths involved in their electromagnetic radiation doesn't have a whole lot of diversity. So it seems like there should be a fairly finite set of parameters that could be used to kind of analyze these types of situations. And verify, if we could use the simulation data that we have or can create quite easily, and then verify those results through outdoor testing, that would be a very significant achievement and very useful achievement. Okay. But it's not yet helping us in the computation. The second part would be if I go back and look at this picture. As I said, what takes me so long is that I need to run something like 100,000 of these where I change the position of the source. So if I think of this as sort of a 3D data cube, it seems to me that here, if I could run a subset of these simulations and use those as my random measurements, I should be able to generate some of the other ones using kind of compressive sensing techniques. That strikes me in my gut as something that sounds reasonable. Okay? I don't know if that's true. I'm looking for feedback. Okay. So that, I believe, this one seems very hard, which is on a given simulation. I'm tracing something like 500,000 rays as I step through this thing. 500,000 rays don't intersect all my receivers. Okay. So I know that I'm putting a lot of time and computation into stuff that I don't need. Now, can I pick random sets of these rays and get the information? I don't know. But it seems to me that it would be a very interesting, although it seems to be very hard, problem to try to actually use compressive sampling type of technology to figure out which rays or how to pick rays so I can actually take the time for a single simulation. So I think the combination of certainly of this and parallel computing could get us close to solving it in my lifetime. I think I have 50 years left. Okay. This one I don't know about, but it sounds like I think it's a really interesting character to go after. Okay. So in conclusion, accurate RF propagation is really important. It's important in military communications and situational awareness. Improving this will save lives. If it's good for the military, it'll also be good for police, fire rescue, emergency responders. They have to work in urban situations. 9/11 is a good example that people in the stairwells can't communicate. Firemen in the stairwells can't communicate to the guys outside. Complete solution to this problem would be really useful for emergency 911. If I had a complete map of what kind of intensities I would expect from different cell towers, I would get very accurate location of the call. And then there's commercial applications. Obviously, most of the money is there, but you have to have very high readiness to be able to go with it. The shooting guns and rays techniques are very accurate, but their computation is expensive. And it looks like to me that the compressive sensing techniques look really well suited to relating some of that computation. So that's what I have. Yeah. Happy to take some questions.
What frequency range are you considering?
Well, military comms band goes up from 200 megahertz up to about 900, but we might go up into the L band, 15.
So just, a question. Do you think that, I think the first question is, do you expect to have some sort of a time stability, let's say on a practical setting? If you are to do measurements now and let's say in a minute from now, or
Right.
what's the time scale?
Well, certainly for
Stability
what we would
first.
call predictable shadowing, the buildings aren't going to move. There would probably be some jiggle on it, but I think it would be stable around a value. So if you integrate long enough, I think that there would be a reasonable value for the predictable shadow.
Right, but are you actually looking at the intensity, like received power, or the actual phase of the signal?
Well, with the ray tracing, I can do both.
Right, but which one are you actually interested in?
Well, I'm actually interested in both, but I'm more interested in the received power.
Received power, right? And at what, I mean, if you do the ray tracing, how many rays do you think that you need to consider to get at the same level of accuracy, let's say, or uncertainty compared to, like through building or some other type of propagation that you might not
Typically,
other simulation?
for the ray tracing, when I'm looking at 5-meter receiver intervals, I need to be somewhere around 0.3 degrees. Every 0.3 degrees are the ray tracing, so what was that, 40,000? Somewhere around 400,000 rays.
And if I may, one more question.
Sure.
So in terms of predictable, let's say channel identification. So I mean, some typical solution is to use like a calibration type signals to calibrate this the channel. So do you think that that might be a solution to
Well,
actually?
it is a solution as long as the calibration holds in the area. Now, and right now that's actually what we implement in deep speak. I mean, we do some channel sounding back and forth between the 2 points they're talking. But as soon as this guy moves, and if you buy a corner or something like that, that calibration may or may not be valid. Like I said, turning a corner, you only move from line of sight to just off line of sight can be a sudden 30 dB drop. So in that case, calibration has limited effectiveness. You have to make sure that you're calibrating every time you hit one of these big barriers.
Any other question?
For this synthetic speech processing, is this specifically geared towards English language, or is
The development has been specifically geared to English language. The principle should be extendable to other languages. Now, the phoneme set from language to language will be different.
Okay.
And so, if we're in something that has a lot of sounds, and I think some of the stuff in the African continent will have more sounds than European, North American, and even Asian. And so you would need a bigger data set of phonemes. But it's applicable to any language. I mean, really, it's just breaking down to sounds.
Just out of curiosity, what kind of data structures would you be using to accelerate the ray tracing? Because it seems like modern techniques, like if you're doing things in massive parallel, like say on a GPU, and then you have an efficient data structure, I mean, modern numbers quote millions of rays per second.
I'm not sure, I don't know what's under the hood with these things. I really don't. I know that there's a lot of graphics array processing and that type of thing. But supposedly what we have is supposed to be state of the commercial art. It's not state of the research art. So I couldn't really comment to what's underneath there.
Okay, let's thank the speaker.
Bradley?